Okay, so at the previous lecture, we began to discuss topological vector spaces. Let's recall that we are mostly interested in those topological vector spaces which are locally convex. Locally convex means that there is a base of neighborhoods of 0 consisting of convex sets. And we proved, well, proved modulo a few simple exercises that topological vector space is locally convex if and only if its topology can be generated by a family of seminorms. So this means the following. If we have a vector space, X, and a family of seminorms P on X, then we consider the family of all balls of the following form. So UP epsilon of X is the set consisting of those elements Y such that P of Y minus X is less than epsilon. So if we consider all such open balls for all X, for all seminorms P in our family, and for all positive epsilon, then the resulting family is a subbase of a certain topology, and this topology is called the topology generated by our family of seminorms P. So we proved that a topological vector space is locally convex if and only if there exists a family of seminorms P such that its topology is generated by P in this sense. That is, the set of such balls is a subbase of our topology. Okay, so at the end of the lecture, we proved the following useful continuity criterion for the linear operator between locally convex spaces. Let's recall the statement. Suppose that we have two locally convex spaces, X and Y, and we assume that P is a defining family of seminorms on X, so that is the family which generates the topology on X, and Q is a defining family of seminorms on Y. So we have two locally convex spaces and a linear operator T from X to Y. The following conditions are equivalent. Condition 1, T is continuous. Condition 2, for each seminorm Q from this second family, Q composed with T is continuous. By the way, this is a seminorm on X, and this seminorm is continuous with respect to this topology. In condition 3, for each Q in the second family, there exists a constant C, a positive constant, and a finite family of seminorms from this set, such that we have the following estimate. Q of T of X is less than or equal to C by the maximum of Pi of X. And this holds for all X in X. So this is our main criterion of continuity. Observe that in the case where X and Y are norm spaces, then what we get is just the well-known statement that a linear operator between norm spaces is continuous if and only if it is bounded. So this estimate means exactly that the norm of T of X is less than or equal to a constant times the norm of X, the norm of X. That is the usual definition of a bounded operator. Okay, now as the first application of this result, let's discuss equivalent families of seminorms on a vector space. So suppose that X is a vector space, just a vector space without any topology, and suppose that P and Q are two families of seminorms. two families of seminorms on X. And we say that Q is dominated by P, and we write the following symbol. If Q determines the topology of Q determined by Q is weaker than the topology generated by P, in the sense that each open set in tau of Q is open in tau of P. So this topology is weaker or coarser than tau of P. And we say that Q and P are equivalent. Q and P are equivalent. And write the following symbol if they generate the same topology on X. Now we have the following corollary from this continuity criterion. The following conditions are equivalent. Condition 1, Q is dominated by P. Condition 2, each seminorm Q in the family big Q is continuous with respect to the topology generated by P. And condition 3, for each seminorm in the second family Q, there exists a constant and a finite set of seminorms from P, P1 to Pn, such that the following inequality holds. So Q is dominated by the finite maximum from 1 to n. Well, why is it so? To prove this corollary, we consider the following simple operator. That's denoted by I. So it acts from X equipped with the topology tau of P to X equipped with the topology tau of Q. And said theoretically, this is the identity map. But only said theoretically. I don't call it the identity map because we have two different topological vector spaces. So the topologies are different. So let's now observe that condition 1 means exactly that I is continuous. It is continuous if and only if the preimage of an open set is open, or equivalently if each set which is open here is also open here. That is, this is equivalent to this inclusion. So condition 1 means that I is continuous. And now we apply our theorem. We apply our theorem, and we see that the continuity of this operator is equivalent to condition 2 and to condition 3. So this is just a special case of our theorem. Okay, let's now look at some concrete examples of equivalent families of seminorms. First of all, we can easily construct stupid examples. For example, we can take an arbitrary family of seminorms and multiply each seminorm from this family by 2, or by any positive number. Then it's clear that the new family will be equivalent to the old family. But this is not very interesting. So let's consider a more interesting example. Let's denote by dr bold dr, the open disk on the complex plane of radius r. Here r is a positive number or plus infinity. So if r is plus infinity, then dr is just the whole complex plane. And we consider the space of all holomorphic functions on this disk, and we denote it as follows: script O of dr. So this is the set of all, the space of all holomorphic function on the disk. And let's consider the following two families of seminorms on this space. The first family P, actually we already know about this family. This family is indexed by compact subsets of the disk. And each seminorm from this family is given by the supremum over this compact set K. We discussed this family when we considered the standard topology on the space of continuous functions on the topological space. So this family determines the topology of compact convergence, the topology of uniform convergence on compact sets. And the same seminorm, of course, can be considered on the space of holomorphic functions. And it generates the standard topology on this space. And let's now consider the second family, defined as follows. For each number r, positive number, which is strictly smaller than big R, we define a seminorm on the space by the following formula. This is the sum of the following series, where Cn of f is just the nth Taylor coefficient of f at 0. Cn of f is the nth Taylor coefficient given by the following well-known formula. So it follows from elementary complex analysis that this series indeed converges, because r is strictly smaller than big R. And clearly this is a seminorm, or in fact a norm. This is a norm in our space. And now let's consider the family of all such norms, and let's denote it by Q. So Q is the family of all norms of this form, where little r runs between 0 and big R. I claim that these two families of seminorms are equivalent. Well, indeed, why is it so? First of all, let's show that P is dominated by Q. P is dominated by Q. We take an arbitrary compact set K. In the disk, and find a positive number r, smaller than big R, such that K is contained in the closed disk of radius little r. This is always possible by compactness, by the compactness of K. Then, for each point in this compact set K, we can decompose f. We can look at the Taylor decomposition of f at 0. And we estimate this as follows. It's less than or equal to Cn of f. And now z is strictly small, less than or equal to r. The absolute value of z is less than or equal to r. So we can estimate this as follows. But this is nothing but this norm, Fr. Okay. So now we take the supremum over K, and we conclude that this semi-norm is less than or equal to this one. And it shows that P is dominated by Q. And conversely, let's now show that Q is dominated by P. So we start with a positive number R, strictly smaller than big R. And we do the following. We choose and take an arbitrary number rho, strictly between R, little r, and big R. It's essential that rho is strictly bigger than little r. And let K be the closed disk of radius rho. So I claim that that this norm is dominated by the supremum over this closed disk K. Why is it so? Let's recall the well-known Cauchy estimates for Taylor coefficients. Cn of f is less than or equal to the supremum over this disk divided by rho to the power n for all n. This is a well-known fact from complex analysis, and the proof is just to write explicitly the integral expression for this coefficient in terms of the integral over the circle of radius rho. And then a simple estimate of this integral shows that we have this inequality. So by using these inequalities, let's now estimate this norm. So this is the following sum. We now write this sum in the following way. And why is it convenient? This is convenient because this number is less than or equal to this semi-norm because of this inequality. So the whole sum can be estimated as C multiplied by this supremum, where C is the sum of the following progression. And this is finite because rho is strictly bigger than little r. And that's it. So we see that this norm is dominated by this one. Okay, so why is this example interesting? It is interesting because if we take any individual norm from, for example, from Q, then it is not equivalent to any norm from P. And the other way around, if we start with a norm from P, then it is not equivalent to any norm from Q. But the families are equivalent. The families are equivalent. Okay. In fact, there are many other examples of the same sort. You'll find them in our next exercise sheet, which is already on the website of the course. For example, there are several useful equivalent families of seminorms on the Schwartz space, on the real line. Okay, I'll give you one more example, a general example which works for any locally convex space. So before we discuss this example, let's introduce some terminology. If, yeah? We cannot. This is an exercise. Well, when I said that if we start with a norm from here, then it is not equivalent to any norm from here, this is an exercise. This doesn't follow from our proof, actually, but this is true. So the naive conjecture is that maybe this sum, this is a norm, maybe it is equivalent actually to the supremum over the disk of radius rho. But it is not equivalent. It is strictly stronger than the supremum over the disk of radius rho. It is strictly stronger than the supremum over the disk of radius rho, but it is dominated by the supremum over the disk of any bigger radius. That's the point. But this is an exercise, of course. An exercise in complex analysis is to show that this is not equivalent to the supremum over the disk of radius r. Okay. So now we give the following definition. So suppose that we have a family of seminorms, P. P is a family of seminorms on a vector space. A vector space X. We say that this family P is directed. P is directed if for any two seminorms from P and Q, there exists a constant and another seminorm from the same family R, such that the maximum of P and Q is less than or equal to C R. Why is it useful? Well, first of all, let's give a topological characterization of directed families. We have the following proposition. So suppose that X is a vector space. P is a family of seminorms. And little x is a vector in our space. And let's denote by sigma x the standard subbase of neighborhoods of x, which consists of all open balls, up epsilon of x, where p runs over our family and epsilon runs over positive numbers. So by the definition of our topology, this is a subbase of neighborhoods of x. I claim that P is directed if and only if this subbase is actually a base of neighborhoods. If and only if sigma x is a base at x. And in fact, it's enough to consider only 0. If and only if sigma 0 is a base at 0. So this is a convenient property. A base is always better than a subbase. Also, if we come back to this continuity criterion for a linear operator, we see that if the family P is directed, then this finite maximum is dominated by a single seminorm from the same family. So this condition can be simplified. So for each Q, there is a constant C and a seminorm, only one seminorm from P, such that Q of T of x is less than or equal to C P of x. So instead of a finite maximum, we can consider only one seminorm from P, provided that P is directed. Направленное семейство. Okay, so directed families are better, are more convenient than arbitrary families. But on the other hand, we have the following result, proposition. Each family of seminorms each family of seminorms is equivalent to a directed family. The proof is very explicit. In fact, there are many concrete families, directed families, which are equivalent to an arbitrary family. So if P is a family of seminorms, then it easily follows from our earlier results that P is equivalent to each of the following direct families. I'll write only 3 of them, but we can write other examples. For example, we can consider P1, which consists of all finite sums of seminorms from P. We can also consider, for example, let's denote it by P infinity, which consists of all finite maxima of seminorms from P. Another family, let's denote it by P hat, consists of all seminorms P which are continuous with respect to the topology generated by our initial family big P. So it follows from our criterion of equivalence of seminorms that each of them is equivalent to P. Clearly, each of them contains P. And so each of them dominates P. But on the other hand, each seminorm from any of this family is dominated by a finite maximum, and dominated by a finite maximum of seminorms from P, and so actually they are equivalent. And it's also clear from this qualities that each of them is direct. This is just this is closed with respect to finite maxima. This is also closed if you have 2 families, 2 continuous seminorms, then their maximum is also continuous. And the maximum of 2 such finite sums is less than or equal to their sum. So this is also directed. Okay. By the way, let's observe, this is a short remark, that the last family from this proof, namely P hat, is the largest family, of seminorms, which is equivalent to P. For the simple reason that if we have an arbitrary family of seminorms which is equivalent to P, then of course each seminorm from this family is continuous with respect to tau of P. This follows from this criterion, from this corollary. Okay. Well, that's all I wanted to tell you about equivalent families of seminorms. Now we are ready to discuss the reason why locally convex spaces are better than arbitrary topological vector spaces. In fact, we already know about one of the advantages of locally convex spaces. Namely, when we work with locally convex spaces, we have 2 equivalent languages at our disposal. Namely, the language of neighborhoods of 0, the language of general topology, and the language of seminorms. The language of seminorms is very useful, and it is not available when we work with arbitrary topological vector spaces. But this is not the main advantage. It's just like a nice user interface for working with locally convex spaces. And the real advantage of locally convex spaces is that each Hausdorff locally convex space has a rich supply of continuous linear functionals. And as a result, there is a powerful and nice duality theory for locally convex spaces, which doesn't exist for general topological vector spaces. Okay, so let's now discuss why this is so. So we'll discuss linear functionals on locally convex spaces. First of all, we give a definition. If X is a topological vector space, then we define the dual of X to be the space of all continuous linear functionals on X. So as usual, K is our base field, that is the field of real or complex numbers. The following result is just a special case of our continuity criterion for a linear operator. But for convenience, let's write it down. So suppose that X is a locally convex space, and P is a defining family of seminorms on X. And suppose that F is a linear functional on X. Then the following conditions are equivalent. Condition 1, F is continuous. Condition 2, the absolute value of F is continuous. And condition 3, there exists a constant C, a positive constant, and there exist finitely many seminorms from P such that the following inequality holds. Also, this is just a special case of our continuity criterion for linear operators. So instead of an arbitrary locally convex space Y here, we just take the base field, and we get this. We now have the following extension theorem for continuous linear functionals. A theorem. Suppose that X is a locally convex space, and X0 is a vector subspace of X. And suppose that F0 is a continuous linear functional on X0. So I claim that F0 can be continuously extended to X. That is, there exists a continuous linear functional F on X which extends F0. We already know that this is true for all norm spaces, and now we show that the same is true for all locally convex spaces. The proof is a simple application of the Unbound Theorem. So we choose a defining family of seminorms, P, For convenience, we assume that P is directed, a directed defining family. Of seminorms on X. And let's observe that the topology on X0 induced from X is generated by the restrictions of seminorms from P to X0. This is immediate from our definition of the topology generated by a family of seminorms. Okay, this implies that if we take our F0 and apply this, this proposition, we see that there exists a constant C and a seminorm P from our family such that F0 of X is less than or equal to C P of X for all X in X0. So since our family P is assumed to be directed, we can choose a single seminorm satisfying this inequality. Okay, and then what we do next, we just apply the Unbound Theorem to F0. And we get a linear functional on X which satisfies the same inequality everywhere on X. So by our previous proposition, this function will be continuous. So the Unbound Theorem yields F. Okay, so this completes the proof.
If it's true for X0, then why is it immediately true for X?
What? By the Unbound Theorem. So what is the Unbound Theorem? If we have a vector space X, a seminorm defined on X, and a functional defined on a subspace X0, such that this functional is dominated by this seminorm, then the Unbound Theorem states that we can always extend this functional to the whole space such that exactly the same estimate holds everywhere on X. So this is just the Unbound Theorem. So by the Unbound Theorem, we can always extend this functional in such a way that the extended functional satisfies the same estimate everywhere. That's the point. And by this proposition, this is equivalent to the continuity of F with respect to our topology. Okay, let's now look at some corollaries. Corollary 1 says that if we start with a Hausdorff locally convex space, then we have sufficiently many continuous linear functionals. More exactly, if X is a Hausdorff locally convex space, then for each non-zero element in our space, there exists a continuous linear functional such that this functional doesn't vanish at X. Equivalent to this means that continuous linear functionals separate the points of X. To prove this result, let's recall that, well, again, we choose a defining family of seminorms, P, a defining family of seminorms. And let's recall that since X is Hausdorff, we can always find a seminorm from our family which is strictly positive at X. There is a seminorm P from our family such that P of X is non-zero, or equivalently is strictly positive. And now we do the following. We define our functional on the one-dimensional space spanned by this vector. We define a linear functional, f0, on the one-dimensional space kx, such that this functional takes a little x to p of x. So it is seen to be continuous, because if we now take an arbitrary vector y in this one-dimensional space, so y has the form lambda x for some number lambda, and this implies that we have the following. The absolute value of f0 of y is equal to p of y. And this implies that f0 is continuous. F0 is continuous. And now to complete the proof, we apply our theorem. We apply our theorem and we get our functional f. Okay, this is a very nice property of locally convex spaces, and actually this is the main advantage. This answers this question. This corollary answers the question why locally convex spaces are better than general topological vector spaces. Of course, the assumption that X is Hausdorff is necessary, because if X is not Hausdorff, if we have a non-Hausdorff topological space, then continuous functions don't separate the points. So this assumption is, of course, necessary. But the assumption that X is locally convex is also necessary. There is an exercise in our exercise sheet 3, which shows that there exist very nice metrizable, complete metrizable topological vector spaces such that the dual space is trivial. That is, there are many examples of topological vector spaces, Hausdorff, metrizable, and so on, such that there is no non-zero continuous linear functional on such a space. So some of them are contained in the exercise sheet, but in fact there are many of them. Yeah, yeah. We can slightly generalize this corollary. Before we do it, let's briefly discuss quotients of locally convex spaces. So we have the following proposition. Suppose that X is a locally convex space. Suppose that X0 is a vector subspace. And let's denote by Q the quotient map of X onto the quotient of X modulo X0. So we take the quotient of X modulo X0 and let's equip it with the quotient topology. We equip quotient with the quotient topology. So by definition, this means that a set U in the quotient is open if and only if the preimage under Q is open in X. So the quotient becomes a topological space. I claim, first of all, that it's a locally convex space. The quotient becomes a locally convex space. Also, we can easily construct a family of seminorms which generates the topology on the quotient. So suppose that P is a directed defining family of seminorms on X. Then the topology on the quotient topology, is generated by the family of all quotient seminorms P hat, where P runs over P. So here P hat is the quotient seminorm of P. By the way, it is essential here that P is directed. Quotient seminorm, thank you, let's recall the definition. So P hat is given by the following formula. This is the infimum of P of x plus y, where y runs over x0. So this is the definition of the quotient seminorm. And finally, part 3. We will also need that. Maybe we don't need this. Just a moment. Let me recall if we really need part 3. Well, maybe no. It's enough. It's enough to know that this is a locally convex space and that the topology is generated by this family. The proof is a simple exercise for you. So if you remember how to do this in the case of normed spaces, then essentially the same argument readily extends to locally convex spaces. The only difference is that instead of a single norm, we consider a directed family of seminorms. But the argument is essentially the same. Okay, and now we apply this construction. And we get the following generalization of corollary 1. Oh, no. Another property of quotients which we need, and this is also part of the exercise. We need a criterion for the Hausdorff property of the quotient. And I claim that the quotient is Hausdorff if and only if x0 is closed in X. In the case of normed spaces, this means just that if you have a semi-normed space, then the quotient is Hausdorff if and only if x0 is closed. Or only if the semi-norm is a norm. And x0 is closed. Well, it's not necessarily a norm, but the quotient semi-norm is a norm. The quotient semi-norm is a norm if and only if x0 is closed. This is a standard fact about normed spaces. And this generalizes this fact to locally convex spaces. Okay, now we apply this to linear functionals, and we obtain one more corollary of our extension theorem, corollary 2. Corollary 2. Suppose that X is a locally convex space, and x0 is a closed vector subspace. A closed vector subspace of X. I claim that for each element in our space which does not belong to x0, there exists a continuous linear functional f on x such that f vanishes at x0, but f doesn't vanish at x. So in some sense, this corollary states that we can separate a closed subspace from any vector which is not in this subspace by means of a continuous linear functional. In the special case where x0 is trivial, we get corollary 1. So corollary 2 generalizes corollary 1. But in fact, it can be easily reduced to corollary 1 by considering quotients. So we take the quotient. Since x0 is closed, we see from this proposition that the quotient is Hausdorff. So we apply corollary 1, and we see that there exists a continuous linear functional g on the quotient such that g doesn't vanish at q of x. Because q of x is a non-zero element of the quotient. To complete the proof, we just let f be g composed with q. This is a continuous linear functional on x. It vanishes at x0 because q vanishes at x0, but it doesn't vanish at x. Okay. Now our next goal will be to discuss the basics of duality theory for locally convex spaces. The central notions of this theory, of the duality theory, are dual pairs and weak topologies. Dual pairs and weak topologies. So we start with the following purely algebraic definition. A dual pair of vector spaces formally it's not a pair, but it is a triple. A triple where x and y are vector spaces. X and y are vector spaces. And the angle brackets denote a bilinear form on the product of x and y. Bilinear form such that this form is non-degenerate in the following sense. First, for each non-zero element x in the first space, we can find an element in the second space, little y, such that this form doesn't vanish at xy. And the second condition is symmetric to 1. So for each non-zero element, little y in y, we can find an element in x such that the same condition holds. So this is the definition of a dual pair. if we have a dual pair, then this bilinear form is usually called the pairing between x and y. And we will use the following short notation. Instead of writing this triple, we write x and y in angle brackets. This is just a short notation for a dual pair. Okay, let's make some simple observations which are immediate from the definition. The first observation is almost trivial, but in fact is very useful. The observation is that this definition is symmetric. Namely, if we have a dual pair, x and y, then we can interchange y and x. And y and x also form a dual pair. So the pairing between y and x is given by the same formula. This is trivial. It trivially follows from the definition, because the definition is symmetric in x and y. And the second observation, so before we do it, we will need some notation for the algebraic dual of a vector space. That is, for the space of all linear functionals. In linear algebra, the algebraic dual is usually denoted by star, but we have already reserved the star for the topological dual, that is, for the space of all continuous linear functionals on a topological vector space. So to avoid confusion, let's denote the algebraic dual of x by x hash. So this is the space of all linear functionals on x. Then the observation is that if we have a dual pair, then y becomes a subspace of the algebraic dual of x by means of the following embedding. So each vector little y goes to the following linear functional on x. And symmetrically, x becomes a vector subspace of the algebraic dual of y by means of the following embedding. So these maps are embeddings. This follows from our axioms. Okay, so taking into account this observation, we will follow the standard convention that once we have a dual pair, we always identify x with a subspace in the algebraic dual of y, and y with a subspace of the algebraic dual of x by means of these two maps, of these two embeddings. Let's now look at some examples of dual pairs.
We say that in the definition of dual pair that this pairing is symmetric.
Symmetric in the sense, well, it's not symmetric in maybe this is not the best word to describe the situation, but I mean that if we interchange x and y, then again we get a dual pair. So
I mean, there you write y, x equals x.
by definition, we define a pairing between y and x by means of this formula.
Ah, okay.
So we just interchange x and y. If we have a pairing between x and y, then this formula determines a pairing between y and x. That's it.
Sorry.
I understand that maybe the word symmetric is not the right word because, well, we know what a symmetric bilinear form is, but this is not a symmetric bilinear form. In fact, it is defined on two different spaces, x and y. But I mean that only that if we have a pairing between x and y, then we can easily construct a pairing between y and x by this formula. Let's now look at some examples of dual pairs. Example 1, if X is an arbitrary vector space, then we can consider two dual pairs, X and its algebraic dual, and we can interchange them and consider X hash and X. And they are dual pairs. And we have a topological analog of this example. Namely, suppose that X is a Hausdorff locally convex space. A Hausdorff locally convex space. Then X and its topological dual, X star, that is the space of all continuous linear functionals, and X star and X. So they are dual pairs. By the way, why is it so? Well, one condition is trivial. If we have a non-zero linear functional f on x, then of course there is an element x such that f of x is non-zero. But the opposite, the second property is not obvious, but it follows from our earlier results. If x is a Hausdorff locally convex space, then for each non-zero element in x, we can find a continuous linear functional which doesn't vanish on this vector. So the fact that this is a dual pair and this is a dual pair is a corollary of our earlier results about linear functionals. If we take a non-locally convex topological vector space, then in general this is not a dual pair. In fact, these are our main examples. So the main reason why we introduce the general notion of a dual pair is that we can apply it to this dual pair and to this dual pair. So the advantage is that of this notion is that if we prove some general result about arbitrary dual pairs, we immediately get two corollaries. The first corollary is about this dual pair, and the second corollary about this dual pair. So I'd like to stress that in general, these two results, these two dual pairs, are not reduced to each other, except for the case where X is a reflexive Banach space. But if X is not a reflexive Banach space, then these dual pairs are not special cases of each other. Okay.
So in case it's not locally convex, then it may happen that X star is just zero.
Yeah.
This
This is not a dual pair. If X star is zero, then one of these three axioms, 1 and 2, fails. If it is not Hausdorff, then this obviously fails because in general, if you have a non-Hausdorff topological space, then continuous functions don't separate the points. So equivalently, if continuous functions separate the points, then our space is necessarily Hausdorff. And in the linear case, this implies that if you have a non-Hausdorff topological vector space, then continuous linear functionals don't separate the points. And
There is this vector that every linear function is 0.
yeah, and we can always find a non-zero vector such that all linear functionals vanish on this vector. And so our dual pair is not a dual pair, actually. Okay. By the way, one more simple observation, which relates dual pairs to the canonical inclusion of a normed space into the bidual. So suppose that X is a normed space. Of course, we can consider the following dual pair, X and X star. And we can look at this embedding of X into the algebraic dual of the topological dual. This is the embedding from observation 2. From this formula. On the other hand, we also have the canonical embedding into the bidual, X double star, which is the topological dual of the topological dual. This is the canonical embedding. So, of course, this space is contained in here. So what I claim is that the diagram is commutative. This is immediate from the construction, but nevertheless, this is quite useful. Okay. So far, when we deal with dual pairs, I'd like to stress that the definition itself is purely algebraic. That is, a priori, there are no topologies on X and Y. But in fact, as we will see now, if we once we have a dual pair, we can always equip X and Y with structures of locally convex spaces. In fact, there are many different ways of doing this. We'll discuss only one of them, which is the simplest one, and which is probably the most useful one. So, suppose that we have a dual pair, X and Y, and dual pair. And now, for each vector Y in Y, we define a seminorm indexed by Y on X by the following formula. So this seminorm on X is given by the following equality. Clearly, this is a seminorm. This is a seminorm on X. By definition, if we now consider all such seminorms, and if we construct the topology, the locally convex topology, on X, generated by all seminorms of this form, where Y runs over big Y, then this topology is called the weak topology. The weak topology. Of the dual pair XY. And this topology will be denoted as follows. Sigma of XY. So the rule to remember this is as follows. Sigma of xy is the topology on X, on the first space, which is defined in terms of the second space. But of course, Y and X also form a dual pair, and we can consider the weak topology sigma of YX This will be the topology on Y. In particular, we have the following two important special cases after we apply this construction to this dual pair and to this dual pair. If X is a Hausdorff locally convex space, then the weak topology on X generated by X star will be denoted like this. And this is just the weak topology on X. This topology is called the weak topology on X. So when we speak of a weak topology on X on a locally convex space, we mean the weak topology generated by the dual space X star. And if we interchange now X star and X, then the respective weak topology on X star is called the weak star topology and is denoted like this. This topology is called the weak star topology on X star. We put the star here to avoid confusion, which can appear in the case where X is a normed space. Because if X is a normed space, then X star is also a normed space. So X star has the weak topology generated by X double star, which is in general different from this one. This is the reason why we call it the weak star topology. Well, in a few minutes we'll discuss the relation between these three topologies in the case where X is a normed space. Okay, let's observe some simple facts about the weak topology. First of all, we observe that the weak topology is always Hausdorff. The weak topology is always Hausdorff. This follows from our main criterion. A locally convex space is Hausdorff if and only if for each vector there is a seminorm. For each non-zero vector, there is a seminorm from our family which doesn't vanish on this vector. So this property follows from the axioms of dual pair. The second observation is about convergence. If we have a sequence in X, then the sequence converges to X with respect to the weak topology, if and only if it converges at each element of Y. So for each Y, X and Y converges to XY. Again, this follows from our criterion. If a topology is generated by a family of seminorms, P, then Xn converges to X, if and only if it converges with respect to each seminorm from our family. And in the case of weak topologies, this is equivalent to this. This is the so-called weak convergence. Weak convergence. Excuse me?
Did we have these criteria on the previous lecture?
Yeah. This was one of the, maybe this was an exercise, but it's quite easy. If we have a topology, if we have a family of seminorms on an arbitrary vector space, and we introduce the topology generated by this family, and then a sequence convergence in this topology, if and only if it converges with respect to each seminorm from this family. This is almost immediate from the construction. If you look at the construction of the topology at the standard subbase for this topology, then you see that this is true. Okay, so this is the so-called weak convergence. By the way, when we speak about some topological property, and if we add the adjective weak, then we usually mean that this property is considered with respect to the weak topology. This is the standard convention. So, for example, the weak closure of a set is the closure with respect to the weak topology. So the set is weakly closed if it is closed with respect to the weak topology. and so on. One more observation explains why the weak topology is called the weak topology. Namely, if you have a locally convex space, X in Hausdorff locally convex space with topology tau, so let's tau denote the original topology on X, then I claim that the weak topology is weaker than the original topology. That is coarser. It has each weakly open set is open. Well, why is it so? Indeed, if we take an arbitrary continuous linear functional f on x and consider the following set uf epsilon of x. So here x is a vector and epsilon is a positive number. So the set consists of all y in our space such that f of y minus x is less than epsilon. So what can we say about this set? First of all, it is open. In the original topology, for the simple reason that f is continuous. F is continuous, and this is just f of y minus f of x. So this is the preimage of an open subset of the base field. If the base field is the complex numbers, this is the preimage of an open disk on the complex plane. So it is open. But on the other hand, we know from the definition of the topology generated by a family of semi-norms, we know that all such sets form a subbase for the weak topology. So on the other hand, such sets form a subbase for the weak topology. And so since each such set is open in tau, we conclude that the weak topology is weaker, not stronger actually than tau. So this explains why the weak topology is called the weak topology. In fact, in most concrete cases, the inclusion is strict. That is, the weak topology is strictly weaker than the original topology. But on the other hand, there are some exceptions in which these topologies are the same. Such examples will be are already contained in exercise sheet 3. Okay. It's time to finish. Okay, so that's all for today. At the next lecture, we continue our study of weak topologies. We prove some results about weak topologies, and then we introduce the general notion of a dual operator in the context of dual pairs. And at the end of the lecture, we prove one of the most fundamental results in the classical functional analysis, which is important already in the case of norm spaces, namely the so-called Banach-Alaoglu theorem, the theorem about weak star compactness of the unit ball in the dual space. Okay, thank you.